In number 11, we're talking about correlation. And the question here is which value of R, which R is the correlation coefficient, which of these two values indicates a stronger correlation? So we're in this chapter here, and you can start to read about correlation. And at the bottom of this page, there's some great pictures of what it would mean to be linearly correlated, what it would look like in a scatter plot. A negative linear correlation, the points would follow basically along a line with a negative slope. A positive linear correlation, the points would follow along the line with a positive slope. And if you're a situation where there is no correlation, the points are just all over the place. And there are situations where we're not going to get into in this course of correlation that's not in a straight line, a linear pattern. And this would be an example of something that has a nonlinear correlation. There's definitely a pattern here, but it's not a straight line. So now talking about the correlation coefficient, which we use the letter R to represent that. It has a complex equation to calculate it. You should rely on technology to calculate this and just understand how to interpret the value you get back for R. It's going to tell us how strong the correlation is and the direction, whether it's a negative correlation or a positive correlation. So if R is equal to 1, the largest positive value it can ever be is 1. And if it's equal to that, it means the correlation is a perfectly straight line. The scatter plot, every single point would be on a positively sloped line. For a correlation coefficient that's close to a positive 1, you'll see an upward linear correlation with your scatter plot. And then as we get closer and closer to 0, away from 1, the correlation gets weaker and weaker. And the variables, the scatter plot of the variables is just kind of all over the place. And so as we get, and going directly down here to this one, as we get even closer to 0, there's no correlation at all. And the points are just all over the place. And now as we dip into the negatives, -1 is as far as we can go. Correlation coefficients are always between a +1 and a -1. And a -1 means we have a perfect negative correlation. The scatter plot, the points are in a perfect line with a negative slope. Things close to -1 for our correlation coefficient, we're going to notice a downward linear pattern in our scatter plot, and there is a strong negative correlation. So to answer this question, this correlation coefficient would represent a stronger correlation because it's closer to -1 than this one is to +1. In these terms, it has a larger absolute value, and a larger absolute value means you're further away from 0. And the further we can get away from 0, the stronger the correlation is. So because it's further from 0, it represents a stronger correlation compared to that correlation coefficient. Correlation does not imply causation. It means that just because two variables are correlated, it is not safe to assume that there is a cause and effect relationship between the variables. There could be some cause and effect, but we can't assume that just because they're correlated. And the book covers this in more depth here. In number 13, we're looking at the correlation between a child's age and the number of words in their vocabulary. We will make our explanatory variable x to be the child's age, and the response variable y is going to be the number of words in their vocabulary. First, we want to find a scatter plot that represents our data. And before we even look at the data, with age as our x-axis, there's only two options that have the correct scale for the child's age on the x-axis, and then the correct scale for vocabulary size on the y-axis. So we've narrowed it down to two results. So looking at our data, you're going to want to copy that into Excel. And here in Excel, you can select all your data, go up to Insert, and what looks like a scatter plot, and just click the first option. In Excel, we'll create the scatter plot, and you can see we have what looks like a positive linear correlation here in our scatter plot. And so the correct choice is the one that's also going upwards with a positive linear correlation. Next, we will calculate the correlation coefficient R. you'll want to right click on one of the dots in your scatter plot and go down to add a trend line. And you see options pop up. Make sure you're on linear. And there's two things we want to click here: display the equation and display the r squared value. We exit out of that and we see those things displayed. Now this is r squared and we want just r, so we need to find the square root of whatever r squared is. So enter that in and you'll get your value here for just r. R is a positive number, which means our linear correlation will be positive. And as R gets really close to 1, the stronger the linear correlation gets. Now, a linear correlation, a positive one, means that as X increases, Y will increase as well, which in this case, positive correlation would mean as age increases, the number of words in a child's vocabulary increases as well. And what we actually want to do to really measure if we have a strong correlation, a significant one, is look at this table of values. So at the 1% level of significance, our sample size was 11. So come down here. This is our critical value. As long as R is larger than that, then it's a strong positive linear correlation. So that's what we're doing here in part D. List the critical value. We're at the 1% level of significance. And since R is larger than that, it's closer to 1, there is sufficient evidence that there is a significant linear correlation. And number 14, looking at the correlation between earnings per share and dividends per share for 6 companies. Now looking at our table of data here, we see our X, our explanatory variable earnings per share, goes up from 0 to a little bit over 8. Dividends per share is from 0, but the largest value is less than 3. So looking at what the x-axis should be, it needs to go from 0 to 9, and the y should be 0 to 3. So there's really just two options here, and we're going to copy our data here into Excel and create the scatter plot to see which is the correct option. So select the data, insert, click on that scatter plot, and you see it looks something like this. And this would be our solution then. The correlation coefficient R, find that next. These points don't look to really be in a straight line, so it probably will not be very close to 1. It'll be closer to 0. Right click on any point and click Add Trend Line. And we have linear selected. We'll click these two options here. And it displays R squared for us. Now we just want R, so we're going to take the square root of what R squared is. And here is what R is. It's pretty close to 0. And values close to 0 indicate that there is no linear correlation. So based on that, there does not appear to be a linear relationship between our two variables, earnings per share and dividends per share. So actually looking at our table here of critical values, we had a sample of size 6, and we want to look at the 1% level of significance. So this is our critical value because we want 1% level. And so there's not enough evidence at that 1% level of significance to conclude that there is a significant linear correlation. And we're saying that because our R value is less than our critical value. It would need to be larger than this, closer to 1, for us to conclude that there is a linear correlation. And number 15, we'll be using a hypothesis test to see if there's a significant linear correlation between the number of hours a student studies, X, and their corresponding test score, Y. When setting up this type of hypothesis test, if you're looking to see if there is a significant negative correlation, your alternative hypothesis would be less than. If you're looking for positive correlation, it would be greater than. And if you're just looking for either type of correlation, you would use not equal to for your alternative. This question is asking, is there evidence of a correlation? It doesn't mention positive or negative, just any type of correlation. So we'll use not equal to as our alternative. We use the t-distribution for this type of hypothesis test. And so our critical value, it's all dependent upon alpha with the t-distribution. Since our alternative hypothesis is not equal to, it's a two-tailed test, so we can enter alpha in here, and then our second input is 2 less than our sample size. So it was 10, so our degrees of freedom is 2 less than that, so it would be 8. And that is our critical value. And so the negative and the positive are our two critical values, marking the rejection region. And now to calculate the test statistic. On top, we just have the correlation coefficient, and on bottom, the square root here, and then 1 minus correlation coefficient squared, divided by 2 less than our sample size. So in Excel, I selected my data and inserted the scatter plot, and then you right-click on any one of these points and click Add Trendline, and you'll want to click down here on Display Equation and the r-squared value on the chart. And that gives you r squared. And to find what r is, then you just take the square root of that value. And now I'm going to calculate the bottom part of that test statistic. You want 1 minus r squared, and then divide by 2 less than the sample size. We're going to take the square root of that result on bottom, so the square root of what I just did, and on top is just r. That's how we get our test statistic. Since the test statistic lies past our critical value, it is in the rejection region, so we will reject the null hypothesis. And no matter whether it was left-tailed, right-tailed, or two-tailed, rejecting the null in favor of the alternative always indicates that there is significant correlation. So there is enough evidence at our level of significance to conclude that there is a significant linear correlation. For number 16, we're looking to see if there is a correlation for soccer players between the amount of weight they can squat and how high they can jump. We're looking to just conclude if there is a linear correlation. We're not specified whether it's positive or negative correlation. So when setting up our hypothesis test, our alternative will be not equal to. We'll do a two-tailed test just to check for any sort of significant correlation. To find the critical values, we use the t-distribution and our level of alpha here. And since we have a two-tailed test with our t-distribution, we use this formula, enter alpha, and then 2 less than the sample size will be our degrees of freedom. We had 12 soccer players, so 2 less than that is 10 for our degrees of freedom. So we have our left and right critical values, and then to find our test statistic, we'll use this formula here, which will rely upon the correlation coefficient r. The value for r is given to us in the problem. In calculating the test statistic, on the bottom part of the calculation, you do 1 minus r squared, and then divide that by the degrees of freedom, which is 2 less than the sample size. So that goes on bottom, but we need to take the square root of it on bottom. So square root of that calculation on bottom, and on top is just r, the correlation coefficient. That gives us back the test statistic. And since our test statistic is past the critical values into the rejection region, we will reject the null hypothesis. The alternative hypothesis corresponds with significant correlation. So since we're rejecting the null in favor of the alternative, it means that we have found significant correlation. So there is enough evidence at our significance level to conclude significant linear correlation.